Hi everybody, welcome back to Matrices 2. We're going to talk a little bit more. So on the last video we sort of talked about how we can add two matrices together. We can multiply matrices. Remember, we have the RC, the row, and the column. We determined ways of figuring out the determinant. So for example, calculating the determinant of a 3 by 3 matrix is kind of tedious. And calculating even larger determinants is even more tedious, unless there are zeros in specific spots of the matrix. So we showed that if there's an upper triangular or lower triangular matrix, or just elements on the diagonal, the determinant is just determined by multiplying the elements on the diagonal. Now, we're going to consider a bit harder example for calculating the determinant. So the reason why I do this is actually later on in the course you'll use Huckle or Huckle Theory to talk about how to find like eigenenergies, for example, for systems in terms of like these alpha and betas, for example. What do we do with this? So this is actually the matrix that sort of represents in Huckle Theory the system for cyclobutadiene. So it's very similar to actually butadiene, except these two elements aren't here. So those alpha and betas are actually what are known as the overlap integrals, or the resonance integrals. And you'll learn a little bit more about those in the course. But for now, we're just going to talk about what to do with this matrix. So with this sort of problem, what we know in Huckle Theory that in order to find a solution, the determinant of this has to be equal to 0. So what we want to show, WTS, is we want to show or find what the energies are equal to. So we're going to do exactly that. So one of the first things we're going to do is we notice that this matrix is a little tedious. So what we can do, one of the rules in linear algebra that you learn, is you can divide any of these rows by like a constant and give back the same row. So what we're going to do is we're going to divide all the rows by beta. So we're going to get something that looks a little bit more simple. So by dividing by beta, we get x, 1, 0, 1, 1, x, 1, 0, 0, 1, x, 0, 1, 1, 0, 1, x. So we denote this x as alpha minus e divided by beta, just so it's a little bit easier to solve the problem. So now we want to calculate the determinant of this 4 by 4 matrix, which is what you've been waiting to do your entire life. So let's do exactly that. So we're going to have to do lots of like minors and stuff. So you're going to have to pay attention to this. So the determinant, I'm not going to write that. Oopsies. We're going to have to scroll back down. So this is going to be quite the process. So don't feel bad, you might have to watch it a couple times if this is all very new to you. So we have x, 1, 0, 1, 1, x, 1, 0, 0, 1, x, 1, 1, 0, 1, x. So this determinant, that's what the bars are representing, is equal to 0. So we're going to calculate the minor for this. So we got this guy, and that cancels out those. So we're going to have x times x, 1, 0, 1, x, 1, 0, 1, x. And then it's going to be minus this 1. We're going to cancel out those. So we have something that looks like 1, 1, 0, 0, x, 1, 1, 1, x. And then the next one is 0. So there's nothing there. And then we have minus 1, 1, x, 1, 0, 1, x, 1, 0, 1. So maybe give yourself a second to catch up if you need to, and again, that's equal to 0 overall. So now we want to get even further and see what these look like. So now we take the minors of those parts. So this is x. This is going to be times. Again, we get rid of that. So x, x, 1, 1, x, minus 1, 1, 1, 0, x. And then the last one's 0, so that's it for that one. Then we have minus 1. That's going to be 1 times x1, 1, x. And then minus 1 times 0, 1, 1, x. And then our last term that we have is going to look like minus 1, 1, 1, x, 0, 1. And then minus x, 0, x, 1, 1. And then plus 1, 0, 1, 1, 0. So maybe give yourself a second to catch up if you need to. And finally, we just have the determinants of the remaining ones to take a peek at. So, let's take this nice and slow. So, the determinant of the first one is going to be x squared minus 1. The determinant of the next one is 1 times x minus 1 times 0, so just we get an x back. Then we have a minus 1, and then x times x minus 1. Then we have a minus 1 times 0 times x minus 1. So minus and minus cancels out to give you plus. And then the last one we have minus 1. 1 times 1. So we have 1. Minus x. And that's going to be times a minus x. So we get plus x squared. And then finally for the last one, it's going to be 0 minus 1. So we have a minus 1. So maybe give yourself a second to catch up again or think about this. Okay, now we proceed and we're going to distribute through some of the x's. So we got x times x times x squared. So we have x to the 4th. And that's minus x squared. We have to distribute that x through here, so it's going to be minus x squared again. And then we have minus this whole guy over here, and these ones, of course, cancel, and so do these. So we have minus x squared, and we have minus x squared. So this gives us x to the 4th minus 4x squared. So now we're going to be looking at something that looks like x squared times x squared minus 4 is equal to 0, right? So what is x? So now you had some time to think about what x is. So remember what we defined x to be. We defined x to be alpha minus e divided by beta. So this solution over here gives us that x squared is equal to 0 and x squared is equal to 4. So we get two solutions then, or three solutions actually. So we notice that the possible solutions are x equal to 0 and x equals plus or minus 2. Oh, sorry, that's supposed to be an x. Okay, so what does this mean? Now we do note one thing before continuing on. We're going to need to go to the next page soon. Pen. There we go. Okay, so we do note that this solution was an x squared. So this term is going to be doubly degenerate. And then we have our plus or minus 2. So we showed up here again that x is equal to alpha minus e over beta. So then we have for one of the solutions that alpha minus e divided by beta is equal to 0. So this simply gives us that the energy is equal to alpha. Now our other solution, we have alpha minus E divided by beta is equal to plus or minus 2. So we see that this energy becomes a little more difficult to calculate. So we notice that it might be easier to sort of think about these separate. So that's what we're going to do. So we're going to consider the positive case first. So the positive case first. We get that alpha minus E divided by beta is equal to positive 2. So alpha minus E is equal to 2 beta, which gives us that this energy is equal to, alpha minus 2 beta. And then for the other one, the minus 2 case, we have alpha minus E divided by beta is equal to minus 2. And then we get alpha minus E is equal to minus 2 beta, which finally gives us the result that E is equal to alpha plus 2 beta. So remember, this one again is doubly degenerate because of the x squared. So our final solutions are going to look like, so we can say for cyclobutadiene, we have the possible energy eigenstates. We have E is equal to alpha and alpha, because it's doubly degenerate. And we have alpha minus 2 beta and alpha plus 2 beta. Now you're going to learn what these alpha and beta mean at some point, but this was basically some good practice to basically determine, hey, how do I figure out some sort of determinant that's a bit harder to think about? Okay, now we move on to a bit of a different topic. So we know that operators can be represented as matrices. So that was mainly one of the reasons for the matrix introduction was that. So we consider a spin 1/2 system. And so we can either have spin up or spin down. We can think of this like a light switch. There are two states. You can have the light switch to be on or off. So in spin it's the same thing. We have the spin up and spin down. These are alpha and beta respectively. Now note, this alpha and beta is completely unrelated to the alpha and beta in the last section. And for example, one of the spin matrices for SZ is h bar over 2 times 0, 1, 0, 0, minus 1. So what if we wanted to figure out, let's say, the eigen, to determine if alpha is an eigenfunction of SZ. So what do we want to figure out next? Okay, so we want to show that SZ operated on alpha returns some sort of constant, let's say A times alpha. So we're going to do this multiplication. Alright, this is what you've been waiting your entire life for. Alright, so h bar over 2, 0, or 1, 0, 0 minus 1 times 1, 0 gives us again h bar over 2. We're going to multiply the rows and columns, so 1 times 1, 0 times 0 gives us 1. 0 times 1 minus 1 times 0 gives you this. And so we see that the value is h bar over 2. So we could do the same exact thing with beta then. So we have SZ hat beta is equal to some constant b times beta. So this is equal to h bar over 2. 1, 0, 0 minus 1. 0, 1. So again, we're going to perform this multiplication. So 1 times 0, 0 times 1, so we get 0. And then here we get 1. Sorry, minus 1. So this is equal to minus h bar over 2 beta. So thanks for watching. I hope you learned a lot about the 4x4 determinant example that we did, and a little bit more about spin matrices and how we can represent them as matrices, and figure out the eigenvalues this way. So thanks for watching. Hope you have a great day, and don't forget to be awesome. Thanks.